Okay, so today we're very happy to have Horacio Casini. The talk is on completeness and generalized symmetries. Okay, please go ahead, Horacio.
Okay, thank you for the invitation to speak. This is based on a recent work with Javier Magan that probably is in the audience, I don't know. And it's based on earlier work with Marina Huerta, Javier, and Diego Pontello of these 2 last years or 3 years. And this last work with Javier, it was devised as a kind of short review, because we thought that what we have said in our papers was somehow useful to things that people were discussing in the last literature. So we decided to do this review, and this is the plan of the talk. The main thing is a proposal for an idea of completeness in quantum field theory. That is the same idea that people have been discussing, but a bit more clear. That it says that the quantum field theory is complete if the algebra generated by local observables in a region is the maximal one that is compatible with causality. Causality meaning here commutativity of observables at spatial directions. And this seems to give a simpler, unified perspective on generalized symmetries and completeness. Both of them are 2 facets of the same idea. In particular, failure of simple properties, additivity or duality of the relations between algebras and regions in quantum field theory is related to, so in our definition is when the theory is not complete, and this leads to multiple algebra choices for the same region and to generalized symmetries. And this clarifies that symmetries, in the sense of generalized symmetries, always come and disappear in dual pairs with the same size in some precise sense. And the entropic order parameters can be defined for these symmetries, can be defined using this non-uniqueness of the choices of algebras. And this entropic order parameter satisfies something that is called a certainty relation that relates the statistics of dual order parameters. And at last, I will try to show some applications. So let me begin by describing the idea of algebras. Algebras are just can be thought as laboratories where one have available some operators that close an algebra. Given a set of operators, we can compute the commutant, that is a set of operators that commute with all operators in A. And this is automatically an algebra. And there is this von Neumann theorem that nicely and elegantly determines in algebraic way what is an algebra is some set of operators which is equal to the double commutant. Here I have to say something more because this is always the case for finite dimensional algebras, but in infinite dimension Hilbert space we have to choose a topology, and these von Neumann algebras are closed on the weak topology. This means that given a set of operators, we have to take also the operators that cannot be distinguished from this set of operators by a finite set of experiments with finite precision, let's say. So it's very physical, and it's unavoidable if you have an algebra of physically speaking, if you have an algebra of operators in Hilbert space to talk about this von Neumann algebra. I'm saying this because people usually think when you talk about von Neumann algebras, you are hiding something there that maybe not completely physical. Well, it's natural that the set of algebras in Hilbert space have a further structure. Intersection of algebras is an algebra, and you can also take the generated algebra of the two, that is just the union double commutant. You close it with a double commutant. On the other hand, for causal regions in Minkowski space, we have some kind of a structure that is similar. We have a region and we can take the spatially separated set, this W prime, I will call it, that is the causal complement, and the causal regions that look like diamonds are closed in the sense that W is equal to W double commutant. So it's very similar to what happens with algebras. And there is a further structure that intersection of these causal regions is a causal region, and you can also take the causal region generated by the two. So in the quantum field theory, we have an assignation of algebras to regions. I will think this algebra is the algebra of observables that you can build in region R. And then there are simple relations that are obligatory and minimal in quantum field theory. One is that if you have two regions that are one included in the other, the algebras should have to respect this order. So this is called isotony. This is just tell you that the algebras are thought as observables in the region or operators in the region. And this other one, this causality, is just meaning that if you have an operator in a region, it must commute. This is a commutant with the operators in the commutant part, so in the complementary region. The operator in the complementary region commute with operators in the region. And then you can think how to put more axioms into your quantum field theory. And the most thing, the thing that the maximal possible relation between algebra and region, the maximal harmony between algebra and regions, is just extending these axioms to these ones. The first one tell you that is called Hug duality, that is the fact that the operator, this is not an inclusion, but it's an equality, they say. So it's kind of completeness itself, because you have enough operators such in the region R such that they are equal to the operator, the commutant operators in the region R prime. This other condition is called additivity, is that the algebra of the union of two regions is the generated algebra. And this is quite natural if you start with a theory described by fields, because you are producing the local algebras by averaging these fields and then smearing these fields, and then it naturally appears this additivity property. So behind this additivity property is the fact that you have your degrees of freedom are local. And then you have this intersection.
Sorry, can I ask,
property.
this
Yeah.
wedge for the region, is this like something like a causal completion of the union or something like this?
So this is
It's
the
like-
thing. Yeah,
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 what
yeah. Yeah, it's the causal completion of the union. Is this one? Is here. But I'm thinking in this talk, I will think mostly on these regions as pieces of a Cauchy surface. Let's say T equals 0 surface, and then this is just the union. Forget about that. So you can also play with regions in space-time, but let us think you have a T0 slice, so you can think of this as a union, right?
Okay, thanks.
So in particular, I will mix up the idea of, let's say, 3-dimensional and 4-dimensional regions, because they are one-to-one related. You have the T equals 0 slice and the causal region there. So this intersection property, if you have the other two, this intersection property follows, and if you have intersection property and duality, you have also this one. So I will only talk about Hug duality or duality and additivity. I will forget about this intersection property. So this is the most harmonic relation between algebra and regions, and we define this. This is a complete theory. We say the theory is complete if you have all this. So you can say that the local algebras of observables are which are additively generated in any region. This is important. Is the maximal one compatible with causality? And you can see that this postulate is somehow written in Huck's book as a tentative postulate, but he doesn't develop further this postulate, but it's very interesting. In fact, this means that in a complete theory, you have an assignation of algebras regions that respect all the operations, order, union, intersection, and complement, and is an homomorphism of orthocomplementary lattices between the lattices of causal regions and the lattices of operator algebra. So, well, what I will talk about is the case where this is not fulfilled. So let us think we have a non-complete theory. So in that case, you can define an additive algebra for any region, just taking balls in such a way that they cover some region R. This R can be, for example, a topologically non-trivial region. And we cover this, and you generate the algebra of R just taking the generated algebra of all these balls. And this is called the additive net. And this is the minimal possible algebra for R, because the algebra of R must include the algebra of all balls inside, so it's minimal one. And then you can think, well, if I have the region R, instead of taking the additive algebra of R, I take the additive algebra of the complement and make the commutant. So this algebra, maximal algebra of R, is the one that commutes with is the algebra of all operators that commutes with the operators localized outside in an additive way. So this is a maximal algebra which is compatible.
So can I ask a question?
Yeah, sure.
I didn't understand the first equation. Why is this the minimal possible? Why, for example, I had to restrict to BB and balls? Why can't I also include, like, cubes, which are contained in R?
Well, that's correct. Yeah, I'm assuming here something. It's important your remark. I'm assuming here that algebras of topologically trivial regions are already additive. So it doesn't matter if you build them with balls or with cubes or whatever, they are already the same thing. This does not hold always, because it depends. Some theories, for example, generalized fields, you can make something that doesn't respect that. But the problem there is a different one. Is one where you don't have a stress tensor. Then there is no, if you have a fixed region, let's say, you have many different algebras, because you automatically don't have the causal region here. So I will not talk about this type of counterexamples or like queer theories. So I'm assuming that for topologically trivial regions, you have only one algebra, let's say, that is additive within balls or inside. So it's not different if you choose here balls or if you choose here other topologically trivial regions or whatever.
Okay. Thanks.
So I'm thinking more in evaluating what happens for regions R, which are topologically non-trivial. So in that case, if you have this maximal algebra and this minimal algebra, then it must be the case that the maximal algebra is generated by the minimal one, plus some other elements, plus some other operators. And the same for the complementary region. You have these other operators. We will call these operators A and B as non-local operators. People also call it in the literature topological operator. I will come back to this point later. So in this type of case, you cannot choose an algebra. You see that you have more than one choice. The additive and the maximal one are two possible choices. You can choose other algebras also, but you cannot choose the algebra for all regions at the same time in such a way that satisfies simultaneously duality and additivity. For example, this maximal algebra is not additive, and these additive algebra are not do not satisfy duality, because the commutant of this one is a maximal one, it's not additive. So another thing that you can say here is that as this is an algebra, and these ace operators are equivalent classes inside the algebra, algebra, equivalent classes under the action of this additive algebra. These equivalent classes must satisfy some fusion rules. If you multiply two, you have to.
I'm sorry.
Yeah.
Can I ask a question? Yes,
sure.
You said that this you cannot choose the net to satisfy both duality and additivity. What if I have a net, which I guess if the global index is equal to 1, then the max
I'm sorry.
is the same.
Yeah. No, yeah, you are right. But what I'm saying here is that in this case, where the theory is non-complete, you cannot do that, right?
Okay, I see. Okay.
In that case, I'm exactly talking about the case where you have an index different from 1.
Okay, thank you.
I will come to that later.
Okay.
So these classes satisfy some fusion rules, and also you can see that these operators A's and B's do not commute to each other, or not all of them at least cannot commute to each other. I will come back to that again. So it means that these A operators produce some transformation on the B operators and vice versa. So and in this sense, we say that these A's operators act as generalized symmetries on the B's, and the B operators act as generalized symmetries on the A's. And this notion is exactly the same type of thing as people in this paper call generalized symmetries.
Okay, so do A and B's commute?
No, not all of them. Not all of them. It cannot be the case.
Okay.
It cannot be the case that all of A and all of. So, for example, if I would like to produce a net of algebras with a maximal algebra, that would be incorrect because they will not commute at the spatially separated regions.
Okay, thank you.
Sorry,
Okay.
why? Sorry.
Yeah, I just wanted to, if you could talk a bit more about this fusion rules, because this seems like a very powerful conclusion. I mean, what can you say? Do you claim that there's a finite number of A's? What's going on here? Because there's some. Is this kind of intuitive, or is this rigorous? These sums and everything.
No.
Is there some claim that these n's are integers, for example?
No. Well, at the level that I'm talking here, these are ones or zero, let's say, because we have equivalent classes, just as equivalent classes. So it means that the equivalent classes of A and R prime contains the product contains other equivalent classes or not. Or to get a final description is more complicated, I guess. That I'm here only talking about this idea that you have this product of equivalent classes is a product of a lot of operators inside the algebra, so it can also be decomposed in equivalent classes. And the type of fusion rules you can get is something that will depend on many things. It depends on the theory, but there may be restrictions. I will talk more about that later.
Sorry, by equivalence classes, do you mean equivalence classes modular A additive? Or which equivalence classes?
Yeah, equivalent classes modular A additive. Yeah.
Yeah, but we don't know. I mean, we don't know much about, I guess, in this audience about the structure theorem for this algebras. For example, is it true that you're basically saying that there is some theorem of the sort that every element of the algebra can be decomposed as a sum of elements in some basis? I mean, this seems to be very strong statement. Is there some theorem that you're using of this kind?
I'm assuming something that I first of all, I'm not a mathematician. I'm in the middle. I try to see things in the middle, let's say between quantum field theory and the thing that people have discussed. But what I'm assuming that this maximal algebra and the additive algebra, the inclusion between the two is it doesn't have a relative commutant inside, so it's in that sense, it can be decomposed. So that there is no, but there is no a relative commutant between the maximal algebra and the additive one. So if you take the commutant of the additive algebra and intersect that with the maximal algebra, then it gives you just the identity. What is very natural in quantum field theory in the examples that I will show you is the case.
Okay.
So, I'm defining this completeness as a additivity and duality of the observable algebra, and this is for us is the same as non-generalized symmetries. It's the same thing. So these generalized symmetries are related then to that there is more than one possible choice of algebra for the same region. There is this ambiguity, or if you want, there is a possibility of different choices of algebras for the same region. And this immediately gives you the idea that the generalized symmetries come always in dual pairs. And this is related to the von Neumann theorem, the double commutant theorem. As I review here, if you have the additive algebra is included in the maximal algebra and they are different, then it must happen the same for the complementary region, because these are defined as the commutants of the algebra of the river of the upper line. So it must be the case that they are different. If they were equal, then the upper line would be equal because of the double commutant theorem. So this idea that generalized symmetries always come in dual pairs is completely rigid and solid, and it doesn't depend on the type of symmetry you are talking about, the dimension, the topology, etc. It just comes from this idea. And also, what I said before, the dual non-local operators cannot commute to each other. They cannot commute to each other, otherwise the maximal algebra will be included in the additive one because of definition, because the commutant of the maximal algebra is the additive in the other one. If the maximal algebra of the complementary region will commute with the maximal algebra in R prime, then it will be included in the additive algebra. So this is a simple example. You have a theory with a global symmetry, normal global symmetry, internal symmetry, and you take the orbifold, you take the set of operators that are invariant in this global symmetry. And then in this orbifold, you have these non-local operators assigned to regions with non-trivial topology, with non-trivial homotopy group pi 0, pi d minus 2, dually. The pi 0 region, the non-trivial pi 0 region is 2 volts, for example, and then it's easy to see what these non-local operators are. They are charge operator here, anti-charge operator here. The product of the two belongs to the orbifold, but each of course the charge operators do not, so they cannot be generated additively in the 2 balls. So you need some bigger ball to have this operator inside additively inside the bigger ball. And in the complementary region, the non-local, these operators are labeled by representations of the group, and in the complementary region, the shell outside these 2 balls, let's say, which has non-trivial pi d minus 2, has non-contractible spheres, let's say. Then you have the twists. The twists are just elements, are just operators which implement the symmetry group inside here, but nothing outside. So it's a restriction of the global symmetry group inside the region. This can be constructed in general ways. If you are in the orbifold, you have to construct this symmetrization of the twists. such a way that are invariant, and these are labeled by conjugacy classes. So the structure is that you have the additive algebra of R1 and R2. So without the intertwiners, without the charge-anti-charge operator, you take the commutant, you get the operators that are additive outside plus the twist. And the twist cannot be constructed additively outside. If you have, for example, another charge flux, it should have to be written as something crossing this ball. If you take the additive algebra outside without the twist, then the commutant will include this charge-anti-charge operator. So you have this non-local operator. The other example is the case where your regions have non-contractible loops, and the complementary one, we have a non-trivial P D minus 3. In this case, an example is gauge theories, and you can think, well, Wilson loops, for example, will be non-local operator. Here I have to write it in terms of this non-physical operator, the gauge potential. But it turns out that not all Wilson loops are locally generated not all Wilson loops are non-locally generated in a ring-like region. For example, if you have a representation for which there is a charge operator, then you can produce these Wilson lines that now are ended in some pieces here with charge operators, and with these Wilson lines, you can multiply them along the line of the Wilson loop, and you can produce a Wilson loop additively. And then that happens also with for non-abelian gauge theories. That happens always for the adjoint representation, because you have these FU fields that are charged in the adjoint representation. So Wilson loops produced by the adjoint representation of any of their fusion with itself will always be additive operators in the ring. So will not be non-additive operators. And it turns out then that the non-local classes of Wilson loops are labeled by representation of the center of the group, and dually, there is a dual operator, this B operator, that are the top loops that are labeled by the center of the group. So these are the basic examples that coincide with what people talk about in generalized symmetries. So these are some remarks. First one is this non-local operator is a relative notion. It's a relative notion with respect to the region where you are talking about. For example, a Wilson loop can be non-local in a ring-like region, but additive in a different region. For example, in a ball that contains a ring, you can write the flux of the magnetic field, and then it is an additive operator in the ball, but it's not additive in the ring. This idea people call they are topological operator. In what sense? Well, it is often said, for example, meaning that the Wilson loop is a magnetic flux that does not depend on the surface, but depends only on the boundary of the surface, right? This is one meaning. There is another meaning, is that the same non-local class with respect to some fixed top loop that is linked to the Wilson loop will appear if you move smoothly, deforming the region, the operators by additive operators. So you move a little bit, the Wilson loop still produces the same non-local class, and this idea is called transportability of these sectors. You can deform your regions, and then you still have the same sector. There is an important thing that often, I think, in this area produces much confusion, is this idea of, we call it Haack-Dirac nets because it's related to Dirac quantization condition. The idea is that, for example, you have a Maxwell field, and then or some gauge field, and then you can choose a net that has the additive operators for all the rings, but also have some particulars, non-local operators, in such a way that this net of operators attached to regions satisfies duality by picking particular non-local operators for each region. in such a way that they satisfy Dirac quantization condition. And in this way, it's a local net. Operators attached, non-local operators attached to complementary regions will commute to each other because of the Dirac quantization condition. You can produce a net in this way, but these nets, of course, do not satisfy additivity. So it's not complete, the theory, because you have chosen that they satisfy duality. You have chosen a maximal net in satisfying duality, but it's not additive. So it's not complete in this sense. And there is also the thing that there is nothing physical in this type of choices. There is nothing physical. You have the Maxwell field, you choose some Wilson loops to some rings and some other Toff loops to some other rings, but there's nothing physical. You cannot distinguish any of these choices physically by doing measurements. There is nothing physical at all. What we are talking about, the completeness or non-completeness, is a physical thing. There is another thing that is also confusing, is that the case of ordinary global symmetries, when they are not broken, there is a special, they are special in the following sense. There is the net that I talk about, this orbifold net, or the net of observables, that people in algebraic community call it the net of observables, because charge operators cannot be measured in the laboratory. You don't have a charge or a creating operator in the laboratory because you would violate charge conservation. So but this orbifold net can be completed to a net with charges with the same correlation functions for the neutral part. So this sometimes we do not know how to do that for example, for a gauge theory, for a non-abelian gauge theory, for example, how to complete the net without changing the correlation functions of the operators that are there. So these are also remarks. Maybe this part is remarks on our ignorance, or I would say the ignorance of everybody, let's say. But that is very little is known about the possible fusion rules and symmetry types that are allowed for different regions with different topology in different space-time dimensions. We have this Doppler-Hag-Roberts reconstruction theorem that seems to suggest that for pure two-ball regions, for example, the one that I was talking about the orbifold, two-ball regions in DE greater than 2 always come from a symmetry group, as I said, the non-local sectors being representations and conjugacy classes through the orbifold construction. So it seems to suggest that, but we cannot ensure that because the analysis starts from a different perspective, these ball localized superselection sectors, and not from the violation of duality. So we do not know how to go to this reconstruction theorem only starting from up to now, they say, starting only from violation of duality for two-ball regions. But it seems that perhaps this is the case, that for two-ball regions in dimension greater than 2, you have always sectors that come from a symmetry group. Unless there are other things, maybe other type of generalized symmetries that are mixed with that. Non-local operators for pure for ring sectors and no two-ball sectors. Let's say you don't have a global symmetry there, you don't have an orbifold, let's say, but you have, for example, a non-abelian gauge theory, pure non-abelian gauge theory without charges. They have ring sectors. And these always form abelian dual groups. The sectors, the dual fusion rules are the ones of abelian groups that are dual, and they have these commutation relations that are fixed. These are the characters of the representation B in the element A. And this can be shown in quite a general way. Well, this is just a commentary that ring and ball sectors coincide in dimension 3, so you cannot distinguish what is coming from gauge or what's coming from global there. Well, and there are many examples that people have worked in then with known fusion rules for 2 interval sectors in dimension 2. Well, this is the idea. If you have these generalized symmetries that are dual to each other, as I said, you cannot have one without the other. And you can also see that they will disappear in pairs, either explicitly or effectively. For example, if you have a non-local operator and you want to make it additive, for example, you can think a Wilson loop, and you put charges in the theory with respect to this Wilson loop, and then the Wilson loop is broken into Wilson lines, so it's not more an operator that is non-additive, it's an additive operator, it's not more non-local, and then the commuting dual operator is then not anymore a non-local operator in R prime. What happens is it still exists in the theory, but it's an operator that depends on a surface. Let's say it's a top operator that is a flux over a surface. So it ceases to be topological. And of course, you cannot make non-commuting non-local operators at the same time additive. And this is the way people usually go to the Dirac quantization condition for the charges of monopoles and electric charges. Another comment, well, the case of effective disappearance of these dual symmetries is when, for example, you have some certain non-local operator that for some scales the expectation value goes to 0, disappear. For example, you can think in this case, the intertwiners charge anti-charge operator, and the charges are very massive, and this distance is large. So you can think effectively they do not exist anymore. Then what happens with the twist? There is a twist that is a smear here, very smoothly smear, and because of the distance is large, you can smear it well in such a way that the twist operator has expectation value 1. So it means that this operator acts as the global symmetry group. It just keeps the vacuum invariant, keeps everything invariant, so it's effectively assimilated to a number. So in this thing, people do not think in this way usually in the literature because people is not accustomed to thinking these non-local operators as smear operators. They always think it's as a line operator. For example, the twist here will be a line operator. And then, of course, this line operator will not have expectation value 1. It will have expectation value 0 because it's sharp there. And this is a problem because this sharp operator cannot be assigned to the infrared. You have to assign an operator to the infrared, it has to be smooth in the infrared scale. So it's important to define smear operators when you define a scale. When you are talking about the scales and you want to think about something that is effective, you have to take something that is very smooth in the scale of the infrared theory. So in this sense, the existence of dual generalized symmetries, the fact that once you have a generalized symmetry, you have the dual one in the complementary region, is a macroscopic phenomenon. It is both symmetries exist together or none of them in the effective theory. And when we talk about the effective theory, you have to think about taking, for example, a ring operator, let's say a ring, and then doing the scaling of this ring, and that involves two things, the radius and the width, both of them together. One way to say this this type of idea, or to talk about these ideas better, because what happens here, when you have this ring very large, you have operators inside, for example, Wilson loops that are very sharp. So which one you take inside this ring? You have to take some wide Wilson loop instead of the thin one, but there is an ambiguity there. How to avoid that? You want to talk about the geometry when you do this, instead of talking about particular operators inside the region. So one way to do that is to talk about entropies instead of talking about particular operators. And the idea of these entropic order parameters is that if you have two algebras in the same region, and the fact that you have these two algebras, you can produce two states in the same algebra. I will show how. And then you take the relative entropy between these two states. This is the idea of how you construct this order parameter. For this, one has to introduce this conditional expectation that is a positive map from an algebra to a subalgebra that leaves the subalgebra invariant. Here is just a map from the maximal algebra to the additive one, that essentially what it does is killing the non-local operators. It kills the non-local operators and you get the additive one. And this conditional expectation can be used to lift a state. A state is just let's say it's a device that takes operators and give you a number. So you take an operator in the maximal algebra, you apply the conditional expectation and gives an operator in the additive algebra, and then you take the state in the additive algebra, and this gives you a state in the maximal algebra. Now you have two states. One is the vacuum, and the other one is the vacuum composed with the conditional expectation. Essentially, what I'm comparing here is in the maximal algebra, you are comparing the vacuum and the vacuum where all non-local operators are set to 0. You are killing them. So this is just the two states. And the relative entropy is a measure of distinguishability between two states in the same algebra. So it measures the distinguishability between these two things, and then essentially is measuring the expectation values of the non-local operators in the vacuum against something which has 0 expectation values for the non-local operators. So it's a measure of the statistics of the expectation values of non-local operators, but it also takes into account how they are related to the additive algebras too. And that is why it is a function of the geometry of the region. You don't need to talk about a specific non-local operators. You talk about just the geometry of the region. You have this number that essentially measures the statistics of the non-local operators, but this number will have some idea inside of automatically chooses the one that has a higher expectation value, but because it measures the distinguishability between the two, so it takes the best of it takes somehow not exactly, but heuristically, it takes the best non-local operator and to compare these two states. And there is a way to produce a standard non-local operators using the determined by the geometry and the vacuum using modular theory. That is something that was used a long time before ago by Longo and collaborators, for example, and Doppler to create these twist operators to show that they always exist. Well, then now that we have this conditional expectation, we can write this complementarity diagram. You have the maximal algebra for the region R, the additive one, and then you have this conditional expectation that kills the non-local operators. And in the vertical direction, you have commutants. So you have, for the complementary region now, for the complementary region, you have the maximal algebra, it's a commutant of the additive here, and you have this complementary conditional expectation. And once you have this complementarity diagram, there are these two conditional expectations are called dual conditional expectations, and in the case that I'm talking about, where this you have this relative commutant is trivial, then these conditional expectations are unique in quantum field theory. So everything is very rigid and is very fixed. Once you have this, you can show you have this entropic certainty relation that is just that the dual order parameters corresponding to the dual generalized symmetries in complementary regions, they both add to something that is completely fixed, that is a number. For example, in the cases that I showed that correspond to a symmetry group, it's just the logarithm of the size of the group, the number of elements in the group. In more general case, this can, of course, can be studied outside, also outside quantum field theory. This number that appears here is called the index of the inclusion of the additive algebra inside the maximal one. So it's a number that is purely algebraic, let's say. And it happens that it's exactly the same number you get for the complementary region also. It's the same number, so it belongs to both of them, both inclusions. In that sense, the dual symmetries have exactly the same size if you think this lambda is the size of the symmetry. This was discussed in mathematical context by it's a shown index that later was it was generalized by Longo and other people, and we arrived to this. We call it certainty relation. And now I will say why we call it certainty relation, but this was in our paper here. Then Javier Magane and Diego Pontello studied the general case of finite dimensional algebras, and these two papers contain proof of this for the algebras. In our paper, we did something like a physicist kind of calculation, and then this is just a proof, mathematical proof of this certainty relation in the context of type 3 algebras that appear in quantum field theory. So this entropic certainty relations here is somehow related to uncertainty relation in quantum mechanics. Why? Because these are relative entropies that are always positive. So it must be the case that this is bounded between 0 and log G, and this other one is bounded between 0 and log G. But both of them cannot be log G at the same time, right? Because they both add up to log G, not to log G. And this is what has inside this idea is the uncertainty relations for the non-commuting operators A's and B's that are here. So when is that this is order parameter gets to the maximal one when the non-local operators A get to maximal expectation value, and the same here. They both cannot get to maximal expectation value at the same time. This certainty relation also give you a hand on computations because you have that the other parameter is because of a monotonicity of relative entropy is greater than some relative entropy of the same type, but in a smaller algebra. For example, you can take a set of non-local operators that close an algebra, and then you can compute this because if you know the expectation value of the A operator, you can compute this quite easily. and then it gives you a lower bound, and you can do the same for the other algebra, the corresponding to the complementary region, and you can get an upper bound. So you can sandwich between something that in principle, if you can compute expectation value of non-local operators, you can sandwich this and try to give bounds to this quantity. So returning to the idea that in effective way, generalized symmetries, dual generalized symmetries disappear together. You have to do this scaling, and then what happens is that, for example, if the order parameter to the ring goes to log G, then the other one, the complementary one, goes to 0, and if this goes to 0, the other one goes to log G, and when it goes to log G, it means that these non-local operators get the maximal expectation value, and then they act as numbers. So this is a remark. This is something people have.
Sorry, Horacio, can I ask before you? So are you going to explain how do you actually compute these relative entropies starting just from the expectation values of the local operators?
Oh, here, well, we have done several computations of that kind. If you have, for example, you can compute this thing. This thing is if you need, for doing that, you need expectation values of non-local operators, which in general is not easy because you have to produce these non-local operators and compute the expectation values, of course. We have done it, for example, for free fields or for example, for non-abelian theories in the weak coupling limit. We could do that.
So there is a simple formula to write this S in terms of.
Yeah. Once you have the expectation values, there is a quite simple formula to write this. Of course, you have to know the algebra of the non-local operators. For example, here I'm talking about groups, so it's quite easy to compute this thing. Yeah, I'm not I'm not explaining this calculation, but it's a simple one.
Okay, it's in one of these papers that you were citing before. Or?
Yeah. There is all this calculation. Yeah.
Okay, thank you.
This is the idea that modular invariance somehow is related to completeness for two-dimensional CFTs. For example, in this paper by Maloney and Cardi, if you what they say is that the range entropies for two intervals in a conformal field theory in a circle follows from modular invariance. But what happens with this idea that complementary regions have equal entropy? Well, this is not the case for every theory, because what is equal for a pure global state is not the quality of entropies for complementary regions, but rather the quality of entropies for commutant algebras. This is the real thing, is the quality of entropy for commutant algebras. So it means that if the range entropies of complementary regions are equal, it means that these complementary two intervals in the circle correspond to commutant algebra, so it's a form of half duality between for two interval regions. So in that sense, modular invariance is related to duality for the two intervals. So it's what we are calling this completeness. And this is a paper by Feng Shu where he studied this case and he shows that modular invariance for many models is associated to the index. This index that I was talking about is equal to 1, so it means it's trivial. The inclusion is the same. It's the same. So there is no maximal and additive algebra; they are the same. But people usually say, well, but if you take the torus, for example, the torus and compute the partition function, if I look the calculation in one direction and the other is the same, it must be the same thing. But what happens is that partition function is not in general in terms of observable operators. So for example, if you have gauge fields or in the orbifold, for example, in the orbifold, you are integrating, for example, to do the partition function over charge fields to write the action. But in the orbifold, the charge field is not there. So in order to get the partition function, you have to put twists in one of the directions and sum over the twist in order to project to the neutral state. So in that sense, it's broken the modular invariance. So in that sense, completeness is a form of generalization, let's say, of this modular invariance to different situations. So this is an idea of our paper with Javier that that people was discussing whether in quantum gravity, say in the bulk, for example, in the bulk of an holographic theory, you could have generalized symmetries. And the idea is that you cannot have, and this is our argument, if you have a gauge field, for example, in the bulk, that's giving you one form generalized symmetry, then there is a current in the boundary. It's dual to a current in the boundary, and then with this current you have twist in the boundary. So once you have twist in the boundary, you know that the intertwinees also exist. So it's a simple thing that if you have a let's say the twist operator, you can produce the twist operators, then the intertwinees have to exist, and this charge anti-charge operator exists, and then you can think that this charge anti-charge operator, when they migrate to the bulk, they produce the Wilson lines that break the generalized symmetries. So in that sense, somehow the existence of these generalized symmetries depend on the fact that you don't have charges in the boundary theory, but this charge anti-charge operator at least is unavoidable. So sorry, how much time do I have?
Oh, we're not strict. It's been an hour, but you can keep going for a while.
Okay, it's already an hour.
Yeah.
Oh, sorry. Okay. So I will flash some applications, just some applications that we have been working on. This is for the case of global symmetry. You can compute this order parameter of the intertwiner, say, and it turns out that in this particular case is a difference of mutual information. Because it's a two-ball or two-region thing. This is a difference between mutual informations. This is known for a long time. And then if you compute a particular limit in which the complementary regions touch each other, what you get is that the index is the certainty relation is saturated. So this order parameter has the maximal value that in this case is proportional to the number of boundaries. And this is a nice way to compute topological contribution of the entropy. Here you have the mutual information in the full theory with charges, and here is the mutual information in the theory with the orbifold only. And the difference is just a topological number that depends on the number of boundaries. And recently, Javier published this paper, based a little bit on this type of ideas, proving the asymptotic density of charge states and the equipartition of entanglement. This asymptotic density of charge states was proposed by Harlow and Oguri very recently. where they conjecture that for a theory, a quantum field theory, at high energies, the density of states with a given charge in the sense of a given representation of the group is proportional to this number. dr is the dimension of the representation times the full density of states. And Javier proved it using the certain relation in the term of field double state. You can do that. And it also holds for the large volume limit at fixed density, fixed energy density. The heuristics behind this thing is just that the maximal mixed state in the regular representation of the group, or multiples of a regular representation of the group, is a fixed point diffusion of many representations. This relation here holds when you have a maximally mixed state in the regular representation. And it turns out that if you, at high energies, you can think you have many excitations. And if you take the fusion, it's a lot of fusion of these representations. And it turns out that they will converge to the regular representation in the maximal mixed state. And this is a kind of central limit idea. And well, I will not talk about this, but this also can be rephrased as the equipartition of entanglement thing, a thing that other people have discussed in the literature. So this is entropic order parameters for gauge fields. This is how they behave for, in the normal thing, idea that we think about these things is that you have entropic order parameters for thin and long loops. And then these entropic order parameters behave an area law in the confinement case for the Wilson loop. And for the top loop, it goes to a constant, and vice versa for in the Higgs phase. And in the conformal case, you expect this, that the order parameter depends on it has a perimeter law. And people often discuss this, that this perimeter law is renormalized to a constant because people is talking about line operators rather than smear operators. Here, when you have a smear operators or relative entropy order parameters, this in the conformal case you cannot really renormalize to a constant. The case of the conformal case, while constant appears in the Higgs and confined phases, but only appears when the width of the loop is greater than the gap. And also in that case, it doesn't subsist for exponentially large size of the loop. So there is some nuisances there. So this is the heuristics of the area law looking through the certainty relation. The idea is that you have these black loops that are small, thin, and suppose these loops have a constant law, so you are in the constant law, and they do not interact much with each other, so there is a gap and there is not much interaction between each other. So then you can compute the relative entropy for the set of all these black loops together, and it turns out that will saturate to the maximal value exponentially fast in the number of black loops. It's not a difficult calculation, assuming that the loops are decoupled to each other. And then it means that for this orange region here, your order parameter will go to zero exponentially fast in the number of black loops that you can accommodate proportional to the area enclosed. So this is why it appears like growing like the area, decaying like the area here. Well, this is a recent paper where we have computed these order parameters for weakly coupled non-abelian gauge theories. And the calculation there is difficult because you cannot easily construct a Wilson loop, for example, a smear. We needed a smear and non-abelian. People do not know how to write a Wilson loop that is a smear in a non-abelian theory. And we find a way out of this just thinking in a non-gauge invariant Hilbert space, where you can define these classes of non-local classes of Wilson loops and compute in the weak coupling limit. You can expect to compute things, and you can compute there. So in this idea that instead of talking about line operators or thin operators, you have to look at in the normalization group flow, you have to look at a scaling of the region. If you think what are the phases of the gauge theory in this sense, you have this situation. The relative entropy order parameters for the Wilson loop and Toff loop either go to the maximal or complementarily to the zero value, independently of the precise shape. As you increase the scaling, independent of the shape, for Higgs and confinement phases, where the way they go to saturation is exponentially fast. And if you have the Coulomb phases, they also go to saturation, 0 or log G, but with a power law. This differentiates these phases from the Coulomb phase. And in the conformal case, instead, you have that the values, the precise value of the limit depends on the conformal geometry of the region. So it depends on ratios here in the thing. We expected that this rephrasing this Wilson loop order parameter in terms of relative entropy will tell us something about how to relate the ultraviolet to the infrared, how to some kind of inequality that will tell us, for example, if you have something in the ultraviolet, it will give you confinement in the infrared to prove confinement, but we didn't found yet nothing of the kind. But it's interesting to go in this direction. So, and this is my last transparency, is about something that we're working now on. It's a simple fact that if you have a continuous global symmetry with another current, then it must be the case that this continuous global symmetry leaves invariant all non-local classes of all generalized symmetries. It means that the global symmetry cannot mix with the generalized symmetries. This is because this nether current is a local operator, and then you can see that. And this idea is very similar to Weinberg-Witten theorem. For example, if you have massless particles with spin 1, so photons, which are charged under the sun symmetry, and the photons have non-local classes for rings, for example, then it must be the case that this other symmetry that is mixing between photons or whatever, it doesn't have another current. And something similar is also, the same idea is also related to the Coleman-Mandula theorem, because with a theory with a stress tensor, you cannot have mixing of global generalized symmetries with the Lorentz, the labels of the generalized symmetries cannot have Lorentz indices, cannot mix with the Lorentz symmetry. And a counterexample of this is not a counterexample, it's an example where you have generalized symmetries with Lorentz indices. Is the case of a graviton. A free graviton have sectors for rings which have Lorentz indices, and as a consequence, it cannot have a stress tensor, as is another result of Weinberg-Witten theorem too. And this was published in this recent paper with Valentin Benedetti. So this was all what I wanted to say. Thank you.
Thanks, Horacio. No questions?
Can I ask a question?
Yeah,
Okay,
sure.
So about your loss transparency in the applications, I'm curious about how you use the entropy, what you call entropy certainty relation, to derive this consequence. So, for instance, the Wimberg-Wheaton theorem. Can you say a few words about that?
No, I'm not. We are not using the certainty relation here. This is just. This is different. No, it's just. The reason why this is happening is that suppose you have a continuous global symmetry with another current, you can produce the twists, right? And you know that by definition, let's say our non-local operator in a ring, for example, will be local in a sphere that includes the ring. So you can produce a twist for the full sphere that will move the non-local operator, that will produce a transformation in the non-local operator. But it's a twist for the sphere. But for a theory with another current, you can split the twist in two pieces, one that acts in the ring, let's say, and one that acts in the complementary part. The one that acts in the complementary part has to commute with a non-local operator because it's an additive operator outside. So it must be the case that there is a twist in the ring, or let's say a little bit wider in the ring, that moves the non-local operator in the way you want because of the global symmetry. But that is impossible. Why? Why is impossible? Because this twist generated by another current is an additive operator. An additive operator cannot change classes. An additive operator in the ring cannot change classes. If you are constructing the twist of the global symmetry as an additive operator in the ring, it cannot change classes. It means that it cannot mix with the generalized symmetry. It's a very simple idea.
Okay.
But it's nice that it somehow threads between these ideas of Coleman-Mandula theorem and Wimberg-Wheaton theorem. It's not exactly the same. These theorems are stated in terms of the S matrix, and so it's a little bit different. But the idea is very similar.
Okay, thank you.
I have a question. Can you go back like 2 or 3 slides to the loops going around the torus?
Sorry, here, this one. Yes.
Can you explain the last sentence again? How does the certainty relation come into play here?
Because what I'm saying is that suppose that I'm making an assumption here. It's not that I'm deriving confinement. I'm making an assumption. This is a kind of a heuristic on how the area law appears, or how these two constant law and area law are related to each other. This is exactly what I'm saying. Suppose you have these black rings that your order parameter has a constant law. The top loop has a constant law there. So it means it doesn't change much as you increase the size of the loop. In that case, your order parameter has a constant law, and you assume also that there is a little correlation between different black loops. You have little correlation, and then you can compute in a set of just simple in a set of let's say product states of this thing, how the order parameter behaves not in one loop but in many of loops together. And this computation give you that the order parameters goes to saturation, to the maximal value log G, exponentially fast in the number of black loops that you can put. And the number of black loops that you can put that are uncorrelated to each other will grow with the area law, with the area law of the ring, of the orange ring, because you can put them separated to each other, as many as the area times something. It's just a completely heuristic idea, right? It's not a explicit computation of nothing. But well, this calculation of how this relative entropy on the black part, on the black loops grow is easy to do. Yeah, or relatively easy to do. So and then if your order parameter for the black region goes to saturation exponentially fast, it must be the case that because of the certainty relation, that the relative entropy in the origin ring has to decay exponentially fast. So you can prove that this is constant, the saturation constant minus an exponential. Let's say you can prove that for the full set of black loops.
Mhm. Anything else? Okay, I guess we'll conclude. Thanks again, Horacio.
Thank you.